Okay, so as in the last video, we have discussed about the dependence of the capacitance of a capacitor. Alright, we were known about the general equation only, right? That is C is equal to Q upon V. But with that equation, we have driven the entire equation, right? We have seen what capacitance of a capacitor depends upon, right? And because of this derivation, we have got that capacitance of a capacitor is directly proportional to the area of the plates, and it would be inversely proportional to the distance between the plates, right? Let me revise that entire equation so that it can be more clear to you, right? So we initially considered the two opposite charged parallel plates. The positive plate of the battery stores the positive plate of the capacitor stores the positive charge and connected with the positive terminal of the battery, and negative plate stores the negative charge and is connected with the negative terminal of the battery with provided potential difference V volt, right? These two plates are separated by a very small distance called d, right? And we know that the charge density is equal to what? The charge density, which is represented by sigma, would be equal to charge per unit area, right? And we know that the medium between these two plates would either be air or vacuum, right? We know that the charge stored on the plate of the capacitor would be directly proportional to the potential difference provided to it. So Q is directly proportional to the potential difference. Alright, when we remove this proportionality sign, we have got is equal to, and C is the constant which is known as capacitance of a capacitor, or the ability of the capacitor to store the charges on it, right? So we wanted to have the value of C, so V was multiplying with C here. When it would go there, would be divided by the Q, right? So C is equal to Q per unit V. This was the first equation. We considered this equation as first equation, which is the general equation. The capacitance of capacitor is nothing but is the ability of a capacitor to store the charges on it, or it is the ratio of the charge and the potential difference provided to it, right? We know that what sigma is equal to. Sigma is equal to charge per unit area, which is known as charge density. We want to have the value of charge since we have charge in our general equation, right? So area is divided with this charge here. When it will go there, it will be multiplied with the charge density or sigma. So Q or charge is equal to charge density, which is sigma, into area. Now let's substitute this value of charge into the equation number 1, right? C is equal to, instead of charge we have put sigma into area upon potential difference V, right? This was the equation number 2. We have considered this equation as equation number 2. Now we know that we have already studied this in chapter number 8 when we were discussing about electric fields. We have discussed there about the potential difference. Potential difference was nothing. Potential difference was the dot product of electric field intensity and the displacement, right? And this we have written here. And it is nothing but, you know what, we have now got the value of our V as well, right? So now let's substitute the value of this potential difference in this equation number 2. So C is equal to sigma area, which are the same. Instead of this V, we have written electric field and distance, right? This is distance, this is not displacement, this distance, right? Okay, so we know that what this electric field is equal to. That would be equal to sigma per unit epsilon naught, which is what we call the Gauss application, right? Gauss law application. So instead of this E, let's put the value of this E in the equation number 3, right? This is equation number 3. So substituting E's value in equation number 3, sigma into area upon, instead of E we have written sigma upon epsilon naught into D. So sigma cancel with sigma, sigma cancel with sigma, this E is dividing here, when we go there it will be multiplied. So area into epsilon naught upon D, this was the equation which we have got. And because of this equation we are getting that capacitance of a capacitor is directly proportional to the area of the plates, and it is inversely proportional to the distance between these two plates, right? Capacitance of capacitor directly proportional to the area of the plates, and capacitance of a capacitor is inversely proportional to the distance between the plates, which means if you increase the area of the plates, the capacitance of the capacitor would be increased, and if you would be increasing the distance of the plates, the capacitance of a capacitor would be decreased. Or if you decrease the distance between these two plates, the capacitance of a capacitor would be increased, since they both have the direct inversely proportional relation, right? This was just a revision of the last class what we have discussed, right? In today's class we are going to put a dielectric plate between these two plates, and then we're going to see what our capacitance of a capacitor would be equal to, right? So now let's make a diagram, and let's put a dielectric plate in it. So this is our negative positive plate, two oppositely charged parallel plates, right? Positive, 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 right? We have put a dielectric plate between these two oppositely charged plates, right? So this is what we have, the dielectric plate, right? Wait, I need to make here the negative charges, right? So negative, 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 negative. Now see, the negative plate of the capacitor would store the negative charge and would be connected with the negative terminal of the battery. This is the negative terminal of the battery. And the positive charge of the plate would store the positive charges and would be connected with the positive terminal of the battery, right? This is positive terminal, right? Now we know that the charges will be moving from the positive to the negative, right? Sorry. So now we have put a dielectric plate in it, right? And here of course we have the battery, so voltage would be provided to it, potential difference, right? So now let's write the equation here. If a dielectric is placed between the plates of the capacitor, or between the oppositely charged plates of the capacitor, the capacitance of a capacitor would be increased by ER times, right? ER times. ER is nothing but it is the relative permittivity, whose value is always greater than 1, right? Relative permittivity. Right? So if we have replaced, or if we have placed a dielectric plate between these two oppositely charged plates of the capacitor, the capacitance, the ability of the capacitor would be increased by relative permittivity times, or ER times, which is the relative permittivity whose value will always be greater than 1, right? It would never be less than 1, would always be greater than 1, right? So now our C becomes, initially this capacitance of a capacitor was epsilon naught area times per unit distance. But now if we have replaced, or if we have placed a dielectric plate between these two oppositely charged parallel plates, the capacitance of a capacitor is increased by ER times, right? So now here the final equation would be C is equal to epsilon naught, it is increased by ER times, so into ER into area per unit distance. This is the final equation, right? If we have placed a dielectric plate between the two plates. So our capacitance of a capacitor would be increased by ER times, means the final equation would be C is equal to epsilon naught times ER times area per unit distance, right? So this was all for today. In the next video, we're gonna start the capacitors in series.